going to have something different now. So Nico Kuehn is going to give you beginning or talk about visualization of epistemic uncertainty. So some of you who were at the peer meeting, what, 3 or 4 years ago, was it, Youssef, where Frank Scherbaum went over this? Nico's going to go over this again. Today is an introduction for most of you. We also have some handouts for those of you who want to look at it tonight for your homework problems to figure it out. And then we're going to come back and he's going to show the real application of this stuff tomorrow.
Right, so this is, some of you have probably seen this before, given by Frank. Some of you have probably used this in some kind of way before. And yeah, so today I'm just going to show you a bit what it's all about. So this is part 1, part 2 is tomorrow. Tomorrow is actually going to be the interesting part, because tomorrow is going to be about the results and the application of the ground motion prediction equations. Today I'm just going to give you some basic overview of the theory, and with a very simple example. So the plan was actually to build slowly up to the interesting part and then stop right when it becomes interesting, so that you can have some kind of a cliffhanger. But now that you've got the results before, kind of spoils the surprise a little bit, but I hope it will still be interesting. So this whole thing started out that we tried to map GMPEs from a high-dimensional GMPE space onto basically a flat surface. So basically a paper or the screen. So the questions that we had were how similar are actually different GMPEs, and can we assess this somehow? Can we actually map epistemic uncertainty? And we wanted to do this without looking only at specific scenarios. Because then you have a plot for magnitude 6, then you have a plot for magnitude 7, and then you have a plot for distance 10, distance 50, and then you have a lot of plots with a lot of GMPEs on it, and it's kind of difficult to have the overview. So the kind of motivation was to have some sort of general difference between GMPEs. And regarding this question, I think Frank would probably say yes. I'm a bit more cautious, and I would say we can map something that is related to epistemic uncertainty. Okay, so this is the basic theory, the basics were outlined in this paper, and if you don't understand what I'm saying, which is quite likely, given that I'm not the best teacher, then just look at this paper. And this is one figure from that paper, so this is what we're kind of hoping to get. We have a 2D surface, and then there are, each GMPE is represented by a point, and GMPEs that are similar should be close together, and GMPEs that are not similar should be farther away. Okay. How do we do this? So basically, we treat a GMPE as a point in a high-dimensional space, and we do this by evaluating each GMPE for different settings of predictor variables, so different magnitude, distance, and possibly other predictor variable combinations, and then we're just combining these into a long vector, and this gives us a point in a high-dimensional space, and then we're going to project this HD point into a 2D space. So in theory, of course, the GMP would be in an infinite dimensional space because it's continuous, but we're discretizing it, in this case, at different magnitude and distance values. That this actually works, I try to show with this picture here. So this is from the Amsterdam Library of Objects. And I always forget what the I stands for. This is a picture of a rubber duck, which is photographed at different rotation angles. So in this case, every 20 degrees. And this is actually not so different. So this picture of a rubber duck is not so different from a GMPE, actually. So basically what this is, so this is a 32 times 32 pixel image. And each pixel has a red, green, and blue value. So this means in each picture there are 3072 numerical values. So this is 32 times 32 times 3. And what we're going to do is we're just combining all these numerical values into a very long HD vector. And then we're going to use different methods to plot them into 2D. I hope you can still see the small rubber ducks. So here we've projected this down from this 3,000 dimensional space into 2D using different methods. First one is PCA, the second one is Salmon's mapping, and this one is self-organizing maps. And what you can see is that they're nicely aligned in this, well, sort of line, and that we see here similar images are actually close together, whereas not so similar images are very far away. So in this case, these actually follow the rotation angles. The same is here and here. I don't think these have converged yet, but just for the sake of argument, I stopped it there. This is the simplest method. It also makes the most restrictions. So this is PCA, principal component analysis. This is also relatively simple. This is the most complex one, and this one also takes the most time to run. So I can run this in seconds, and this one runs, depending on how much input I have, an hour, maybe less. So this is why I'm going to show some parts also of PCA. So how do these things actually work? I think probably.
What are those? You have two dimensions. One's what are you plotting on the axes?
Yes. Can you?
No, you can repeat the whole question.
Okay, so the question is, what are we plotting on the x and the y axis? So this is actually the two-dimensional projection of this 3,000 dimensional space. In this case, it's not. I'm going to come to that later. So how does it work? So this is how principal component analysis works. What you do in principal component analysis is you look for the direction of your data which has the largest variance. This would be the first principal component, and then you look in a direction which is orthogonal to that first principal component, and which maximizes then the rest of the variance, which would be the second principal component, and so on and so on. So this, So this is how this looks like in 2D. This is just samples from the two-dimensional normal distribution, which is correlated in, I think, 0.6 or something. And this is the direction which maximizes the variance. And then the orthogonal direction maximizes then the rest of the variance. And then what you do in PCA is you just project each point onto these two components, and then you plot them. In 2D, this is just a rotation. But when we go in 3D, I hope you can actually see these two arrows there. This is basically the same data as before, but now in 3D, and it's a bit, so it's tilted somewhere. But it's still basically a flat surface. And then you again look for the direction, which maximizes the variance, which would be in this direction. And then the second principal component is then the orthogonal direction, which maximizes the variance, which goes in this direction. And then the third principal component, in this case, would actually be 0. Because because we actually have taken care of all the variance in the data that we have. Okay. We can calculate the PCA by calculating the eigenvectors of the covariance of the input data, which is actually very easy to do. And the eigenvalues tell us how much of the data variance is actually explained by that particular principal component. So in this case, when we calculate the eigenvalues of the covariance of the input data, the third eigenvalue would actually be 0, because there's no variance left to explain in this case. What this means is, so this is the example from the rubber duck. So these are the different principal components, and these are the eigenvalues associated with those principals. So the first one is always the largest one, then we have the second largest one, and so on. And this is the amount of variance explained by this particular eigenvalue. So this is the amount of variance explained by the first principal component. This is the amount of variance explained by the first two principal components, and so on and so on. What this means is we are at 64% here. That means if I reconstruct my original image just from the two principal components, just from the two-dimensional point, I get something like this, which is kind of similar to that one, but it is slightly different. So this is basically what we're doing when we're doing PCA. It's just calculating the covariance of the input data, so of our 3,000 dimensional vectors, calculating all the eigenvectors, taking the first two parts of the eigenvectors, and then plotting them. So this is what was plotted before. Simmons maps is a bit more complicated, but it's still very...
Nico, I have a question.
Yes.
Can you go back?
The microphone is there.
Nico, hello?
Yes.
Okay. Don't you have to have like a percentage, minimum percentage on the right-hand side? For example, 41%, 64%. Suppose
Yes.
hypothetically it was 2%, 3%. If you take the first two, you're missing lots of modes.
Yes, right. That's correct.
What's that minimum?
Depends. I would actually say it should be something like 90%. So
Okay.
this is actually the reason. I mean, it is a bit better for ground motion prediction equations, but it also depends a bit on what you're actually plotting. Then you get with the first two at something like 80%. But to really plot this, you should have something probably by 90%. The thing is just, this is just really, really fast. So I can just do this and directly have the results. Whereas for the other ones, it also depends. I might have to run it overnight or wait a very, very long time for that.
I also have a quick question. So maybe I'm really not seeing this, but it all made sense. But how many principal components can you have?
Well, you have as many eigenvalues as you have independent directions in your data. So, for instance, you have 3,070.
Okay, because it's
Yes,
three. Okay.
right.
Okay, thanks.
Right. But in general, so I think in this case, after 10, you explain most of the variance in your data. Okay. Simmons maps work a little bit differently. It's basically what you do is you calculate the distance between your high-dimensional vectors, then you place some points randomly on the plane, and then you perturb those points on this plane as long as the 2D distances match the HD distances. So what is shown here, so this is the high-dimensional distances between the images. So this would be the distance between the first image and the second image, and so on and so on. And these are the 2D distances between the first image and the second image. And then basically the difference between these two distance matrices is your misfit function, and then you just minimize your misfit function. I don't think it has converged, sorry. I don't think it has converged yet, but it doesn't matter for this example, whether it converges for the duck picture or not. Right. Okay, now self-organizing maps are, from these three methods, probably the most appealing, because it's the most flexible and it can accommodate most of the data, but it's also the most complicated of the three. So basically what you do is you start out with a grid of nodes. I call them nodes. And so basically something like this. And this grid always stays the same grid. So that means this node is always the neighbor of these two nodes. And this node is always the neighbor of this node and this node. And each of these nodes represents an image. So each of these nodes actually represents a picture of a rubber duck. And to learn the self-organizing map is you first initialize each node with a random picture. This is shown here, so this is random picture. This is just randomly values for red, green, and blue. What you then do is you choose one of the pictures that you want to organize. So we choose one of our rubber duck pictures, and then we look at all the nodes here, and we select that particular node which has the smallest distance to that particular picture. At first it will be so you calculate the distance between each of these random pictures to that one, and then you select the one which is closest to that picture. So basically you just take the Euclidean distance between the RGB values of these pictures and that one. So let's just assume it's this one. And what you then do is you actually adjust this node in the direction of that picture. So you don't replace it with that picture, but each of these pixels in this random picture gets drawn to one of the pixels there. There's some sort of complicated function how you can do this, but in general you adjust each of the entries in this picture to be a little bit more similar to that one. And you do this not only for this node, but you do this also for all the nodes in the vicinity. And this is where the self-organization comes in. So that means we're actually drawing all this particular region to be closer to that picture. What we then do is we just repeat. We select another randomly chosen picture, choose one of the nodes which has the smallest distance to that particular picture, and then we're drawing that particular node in the direction of that picture. And then we repeat and repeat and repeat until this thing converges. So this is how it looks like in an intermediate step. We have some parts look already quite close to a particular to the rubber ducks, whereas some parts are still very, very random.
You got one question.
Yes.
How many nodes do you have?
So in this case, we have 8 times 10, but this is up to you. So it depends a bit on the application that you have and how many pictures you want to have. Because obviously,
So in GMP, for example?
so later on, I've used 12 times 16 nodes, which turned out to be a good way to visualize the GMPs. Because what you want to have is you don't want to have just as many nodes as you have models, as you have input vectors. Because what you really want to know is I have two things that are really different, then one should end up there and one should end up somewhere else. So you want to have more nodes than models that you have.
When you're associating the second picture with the one closest, do you exclude the one where you had the first picture?
No.
And wouldn't all then be more similar to the one that you have already adjusted?
Well, it depends a bit on how they are, on how the input data actually looks like. But at first, yes, this is also why these regions get first. But then later on, I don't show this, but later on when you really come, so basically what you're really doing here first is just having the overall shape of it. But when you come later to the sunglasses the face of the duck, then everything gets very, very dissimilar. So so in this case actually, so you first kind of get some overall picture of your rubber duck, or the overall shape, and then you go into the details, and then the details will map out somewhere else.
Are you showing the very first iteration?
No. So this, no.
The very first iteration,
No.
pictures of all these. So
Yes,
how do you
right.
adjust? Yeah, 'cause
Well, basically, so there's also some, well, they're not all the same, there's some kind of random.
so there's
this
some
is,
spatial function of
yes,
this.
right. So basically what you,
Spatial function of
yes,
how you
exactly. So
adjust
basically
pixels.
you adjust this, and then you adjust all the nodes in the vicinity. And then there's also some sort of time parameter, which depends on the iteration. That means the distance that you're adjusting gets smaller over time. So at first you're adjusting a very large area into this direction, and then later on you adjust only very, very close ones.
Yes, so my other question is, for this method, does it make sense to, I guess, keep the full generality, or is there any advantage to doing some sort of wavelength filtering? So first you look at coarse aspects of a model, and then you include shorter wavelength aspects of the model.
Could be. So you mean like having something, so not,
Start with the very coarse aspects of the picture, and then as you start reaching convergence, then add in the sharper features.
might be actually. I'm not sure, but it might be. I don't, I mean, well, it might speed up convergence. I don't think it actually changes the result.
Yeah.
Okay. This is then how it looks like in the end. So this is after many iterations. So each of, what you should still keep in mind, each of these nodes is still a picture of a rubber duck, but these are the ones which correspond to the original images that I put in there. So we still see that images that are similar are close together, whereas images which are not similar, like this one and this one, are farther away. The color code, yes, the color code is actually denotes the average distance of one node to the neighboring nodes. So lighter colors are small distances, and darker colors are large distances. So basically, so therefore this one is on average medium far away from the other ones. This one is very close to these one, and this node is actually very far away. Because so darker colors represent, well, you could call them some hills on that map. So dark colors represent large average distance from this node to the neighboring node. The reason being is that this node is actually influenced by everything else. So this is influenced by all the pictures. And if you actually look at this is some sort of average of all the pictures, but this makes it also very dissimilar to every other picture, because you have you're averaging out like the sunglasses and everything. So this also means, what this actually means is that this is a nonlinear representation. So it's not a flat surface anymore. But so in this case it would be something like a half, or yeah, I think something like a half sphere probably, where this is far away and everything else is like located around the circle. So this also means that if you want to go, or if you want to go from here to there, this might not be the shortest distance. So you might actually go there, 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 there. This might be shorter than going the direct way. Or going from here to there, you have to cross this node, which is very, very far away. So it might be shorter to go in this direction. So this makes it a bit difficult to interpret, and I really have problems interpreting this sometimes. It often looks a bit like this, where you have some clear separation, but it does not always look like this, and then it makes it a bit difficult. But the nice thing is that this can accommodate some nonlinear structure. So this is what I tried to show here. So basically, what we're assuming is that we can project our high-dimensional data onto a lower dimensional 2D manifold. And so basically something like this, where we have the sphere, the globe, and then we're just projecting this, which is basically 2D in structure, but it lives in a 3D space. The same thing is here. I don't think you can see that very clearly, but this is some sort of, it's a bit like this Danish roll pastry, so which is still, which is like a roll, but in general, all these points are inherently 2D. So they're just on this roll surface. And a self-organizing map can actually unroll this roll, whereas a PCA cannot. So in a PCA, you just look in the direction of the maximum variance of this data, and then it just gets messy.
Can you repeat the last 2 minutes? Seriously, I'm not kidding.
Okay.
I'm sure.
Well, basically, what we have, I mean, we have, for this rubber duck example, we have this 3,000 dimensional space. But when we actually look at all the different rubber ducks, the points are not randomly in, so they're not randomly. They follow some structure. So, and this is also the case for ground motion. This is why this works for ground motion model. The first part of my vector might be the ground motion value for magnitude 5. The next part is the ground motion value for magnitude 6, which should always be larger than the one for magnitude 6. So there's some structure in this high-dimensional space. And what we do is we exploit this structure in the high-dimensional space by plotting it down to 2 dimensions. We could plot this down to, well, we could actually do this also down to 3 or 4 dimensions, but then we can't really see it anymore. 3 dimensions might work. You can look at a 3D plot, but 4D doesn't work anymore. But so this is basically what we're doing.
So what I'm wondering right now is if you remove, say, 2 of the duck pictures,
It will still work.
does the structure stays the
Yes.
same?
Well, it will probably
The relationship
yes.
between the remaining
Yes.
duck pictures stays
Yes.
the same.
Yes. So well, this is one thing that we tried to look at earlier. It actually works. So if you plot this, or if you make a picture such as this, you can then actually go ahead and fill in a new rubber duck picture. So basically, I mean, these are all every 20 degrees. And then you could actually go ahead, well, it might not work in this case, but then you could go ahead and take a rubber duck picture, which is 5 degrees from one of the models. And then it will probably end up here. It will actually end up there. And this also works for ground. So I did this for ground motion prediction equations. So I fitted this one, and I left one out. And then I tried to find the node which has the closest distance to the one that I left out. And it was exactly where it was when I included it in the map. So this actually works.
So I guess related questions are, I suspect that because you're going to from a high dimension to a lower dimension, you can't actually interpolate. You can't construct an image that's between 2 or some sets of images.
Well, actually, you can. I'm not showing this here, but each of these is still a picture. And if I plotted them, this here would be between this one and that one.
So then the related question is, could you identify missing models this way?
Yes.
Yes, the idea.
Yes. So actually, I mean, the point is, of course, well, we tried that, but the point is you need to have, of course, I mean, you can actually, so each of these, if I now identify these with the GMPEs, each of these would actually be a GMPE. Each of the nodes, even the ones which are not plotted, would be a GMPE. And so this is a way to interpolate between GMPEs. But they all have the same structure, so I'm coming to that later. They all have the same, it's the same length of the data. So that means if you have some different data, you still need to figure out how to get your data into this structure there.
Question
Yeah, there was also earlier guys waiting.
This might be a trivial question. Am I on? Yeah. So, okay, maybe I'm not understanding completely, but you map all the how similar different things are in all the dimensions. But say you want to look at particulars, how do you interpret this? Like if you are doing the ground motion models, but then you want to say, okay, now I only care about this magnitude range and this distance range and this type of fault. Could you use that stuff to understand details?
Probably, yeah. Well, it depends a bit. I mean, if you're only interested in one magnitude, I would suggest using a normal plot or residuals. But if you're interested between 6 and 7 and everything that's in between, you just restrict your ground motion model.
Okay, to have these dimensions.
I think,
yeah. Okay.
So my question has to do with the physical meaning of the axes in the two-dimensional plane. So in the case of the rubber duck, as we go around, it has pretty clear physical meaning. You're basically rotating around and seeing it from different angles. In the case of a GMPE, I understand that each pixel is a GMPE.
Yes, I'm coming to that later.
Yeah.
Yes, because
hold off on that one.
I mean, this was just to show that it actually works, that it actually finds similar pictures similar together, and I'm coming to that. This is a very, very difficult question, but I'm coming to that later.
So I'll follow up later.
So, yeah, we're pushing the edge of what our time is. So.
Yeah, I'm really, really sorry about that.
Okay, this is why we did this over a couple days, but I want you to...
Oh.
Sorry. Is that better? No? That's better. The idea here is you're going to see this today. Take your handout and start to look at what the pictures are. So it does take a little of Nico's surprise for you, but study it tonight and talk about it. And then when we get back, he's going to go over this again, and we're hoping it starts to make sense. Because this is a lot of stuff, but it's a powerful way that we can start to do just what Doug said, find or put in missing ground motion models to better sample our space.
Okay,
So-
quick question, Nico.
Yes.
You said from one point to another point, the closest distance is not just a straight line, right?
It might not be, no.
Then what is the significance of this if it's not straight? So in other words, suppose two adjacent pixels are not closer to each other than...
Basically, okay, this is not maybe not the best way, but I don't have the picture with me today. But so when I did this, I did this only for the NGA 2013 models. And what you have then is you have one here, one there, one there, one there, and one somewhere else. And then you have some sort of dark color around this. So this tells you then, okay, these are actually different models. So there are some, I mean, it depends always on the color scale that you choose, but this is often used to find clusters, for example. So what you might have is, which you don't, well, these are all too similar for that, but what you might have like these three are very similar and very dissimilar from everything else. Then you would have a darker or nodes with darker average distances between these nodes and the remaining nodes. And then you can say, this is a different cluster than everything else. This is the reason for that. This is real, so it is difficult to interpret. So
Nico, in the paper you talk about mountains and valleys. That makes sense to me, maybe.
yes. Well, so this would be something like a mountain. I don't think this would actually be a valley, this would just be a plain, also would just be flat.
Let me
this,
interrupt you, Nico,
yes.
because we're going to run out of time. This is perfect for sitting around and having a beer and having them explain it to you, okay? This is going to take a while. It's going to take... Right, if you think of it as a topo map, right, or something like that. But let's try to get through 5 minutes and then we'll come back, right?
Okay, so this, well, basically we can... the distances, I'm using Euclidean distances between the points and also between actually logarithms of the ground motion values. From a theoretical perspective, something like the Kullback-Leibler divergence would be preferred because this gives us some sort of, not distance, it's not a proper distance, but some sort of difference between two probability distributions. And we all know that ground motion is a probability distribution. But the nice thing is if we have a normal distribution and the same variance, the Euclidean distance and the symmetrical Kullback-Leibler divergence are proportional. So I can just use this one instead of this one and still have the same information. Okay. So this is, well, it's not really that important. So now we come to GMPEs and how actually GMPE is similar to a picture of a rubber duck. Basically, here we just have pixel with different RGB values. And what I'm using later is a grid of 31 magnitudes and 25 distances, each with a ground motion value. So these are all from 5, so magnitudes are from 5 to 8. And distances are from 1 to 200 kilometers, equally spaced in log space. Okay. And everything else, so this strike slip, vertical strike slip for earthquake, VS30 is set to 760 meters per second, and it's done for PGA 0.2 seconds, 1 second, and 3 seconds.
Nico, you could roll the second bullet to the first bullet also, mixing everything for all the stall of falcon.
Yes, actually you could do this, and this is the plan. You could I decided not to. Well, one reason not to do this is that you're probably going to give different weights for different periods. So therefore you want to have distances for one particular period, distances for another particular. But you're right, then we would just add, so we don't have like a grid, but then we would add the same thing there for different VS30 values and some other ones. The other reason is also that, I mean, in theory, VS30 would be epistemic uncertainty, whereas this is what you're integrating out. So this is also the reason why I'm not including VS30, and also this is just still a little preliminary. But in principle, you could actually put different VS30 values in there and then see everything. Appreciate the whole model. Okay. These are the models, so 14 models, 5 new NGA, 5 old NGA, Aka et al., Reiser and Kalkan, and Zhao et al. There's one model based on the European dataset, which I included because in this case, well, it's not a very good model, and I don't suggest you use it, but in this case, I fitted it myself, which means I can track all the uncertainties in the parameters. So that I can actually plot the uncertainty of this particular model also on the map. This is the reason why this is included. This is actually a sneak peek of the results. So you see there's one outlier, and based on what you've heard this morning, you can probably guess which one this is. Okay, so now we're going to try and interpret this. And so I put in a reference model, which is the mixture of all, in this case, 15 models. And so this is just the average of all the models. And since it's the average, it gets, so this is all Salmon's map now. It gets plotted in the middle. And this is how magnitude and distance scaling looks like. And what I then did is I scaled this mixture, this reference model up and down. So this is basically, so I mean we're all in log scales, so this is the reference model plus log 1.25. And this is the model plus 1.5, plus log 1.5. This is minus log 1.25 and minus log 1.5. And as you can see, they line up very nice on this straight line. So that means when we have later, when all our models lie up on this straight line, then we can say they only differ in like up and down scale. Next, I changed the magnitude scaling of this reference model. You can see this here. I hope you can actually read this. So this would be m++, this would be m+, this is the reference, m minus and m minus minus, which is just, so m++ is the average of all models plus 0.3 times m minus 6.5. And then the m minus is then plus 0.15, and this, no, this is m plus, and then we have minus 0.3 and minus 0.15. And these are, this is a different direction in this map. The same thing, well, I did this for distances, so now I changed the distance scaling, and this is again a different direction. The problem is, of course, we're in 2D, and there are only so many like ways you can go. So this is also a problem if I now included different BS30 values. It's probably, you can't really go in any places. So everywhere you go, you change something. You change both the scaling and the magnitude scaling and the distance scaling. But this is the way to, so this is how we can look at this. That we have our reference model, which is just the average. And then if we have a model which lies like here, it has some sort of different distance scaling. If we have a model which is a different magnitude scaling, if we have a model which is up here, it is a different distance scaling. And if the model lies around here, it will have a different, it's just scaled up or down. And this is then how it looks like when I plot the models on top of that. And so what you see is they're all kind of inside this range that I had before. So inside this range of the mixture model, well, of the reference model, of course, that is right in the middle there, but also inside the scaled and upscaled, downscaled, and changed distance, changed magnitude and distance scaling, except the Bindi et al. Model. And the reason, so this is for PGA. I'm going to come to that back tomorrow, but if you remember what Nick Greger showed, this is just really a really weird magnitude scale. This is why it shows up there. That's not it for today. The same thing, so this is now a bit, this is kind of easy to interpret. And the same thing you can do for the self-organizing map. So here as a self-organizing map, I trained on all the GMPEs. We have the mixture model here, and now since this is a nonlinear representation, we don't have these directions anymore. So this actually means that interpretation gets a little bit more tricky, but we still have that the M minus and minus models are somehow close together. These ones are close together. There's some mountain between the magnitude scaling and the distance scaling. The same here, and we're right. And there might be some kind of mountain here between the ones.
Nico, one quick question.
Yes.
What's the effect of the standard deviation on these distances?
We do not, so the standard deviation is not included here.
This is just the median.
This is just the differences between the median predictions.
We'll get back to this
Okay,
tomorrow.
in few months then you have to include.
Yes.
You have to.
That's correct, but since you're using, well, if you're using the same sigma for all the models, it doesn't matter. Yes.
Tom, make it really fast, because I'm going to have to
And
interrupt
these
you
are
guys.
computed between magnitude 1 and 8, is that right?
5 and 8. Between
5 and
5 and 8. Yes. 5 and 8 and 1 and. So
I need you to jump
yes.
to your end here.
Last one, what I tried to do, but this is of course, so this is actually, so this is called the U matrix, which is the nonlinear representation. What I did is I tried to come up with a map of this by calculating the shortest distance between all the models in this case, and then plotting that again on a map, which looks like this. We still see the same kind of behavior as before. We have 3 main directions, and then when I plot the models on top of that, they look the same. We have the Bindi as an outlier, very, very far away, which is up there. One last thing, so basically, so the distance scaling, so black is the largest distance, but so the thing, so black is the largest average distance between 2 different nodes. That means, that doesn't mean that this is, so this means that black in this case corresponds to a distance of 4, which roughly corresponds to a scaling of 1.125, 1.15 actually. It's actually wrong in the handout. That says 1.25, but it does not. So this, if this is black, it's roughly scaling up or down of 1.15 from the model next to it. Thank
Okay.
you for this discussion, and then just maybe look at this one. Frank is much better teacher than I am.
We're not going to have a test, okay, today, but it'll be tomorrow. So you've got